Okay, so hopefully it was tedious, like I said, but hopefully you have some pretty good numbers here. Even though I said not to calculate the area, I guess if I was kind of an inquisitive kind of person, did anybody just check to see if it was close with your calculator? I think I would have. I didn't say you couldn't do that. I just didn't want the data to be from a calculator. See that? Did anybody do that? Oh, okay. Does anybody know how I would have checked that? Uh-oh. That's not good. Nobody's raised their hand. That's not good. Oh, 2 people raised their hand. All right, Alistair, what do you think? How would you check this?
You would have found the radius, and then just use the area equation, which is area equals pi r squared. Just square the radius multiplied by pi.
Okay, and even though I definitely did not want to see those numbers here, you could at least said, what if you got 256 and the calculation said you should have gotten 356, so you think, I think I did something wrong there. You get that? Okay. Also, I want you to, I like the fact that you have to take your time and be a little tedious. Sometimes we do labs and you have to measure carefully. Measure carefully. All right, here, this graph here, what was on this axis? You just turned it in. Area, and what units were that? Yeah, they were called graph units squared. Weird. And what's down here? Radius in what units? Graph units. Okay, so you've seen that. And you should have seen something maybe like that. Yeah, is that what you got? So we know it's kind of a J-shaped curve. And did you go back in your packet and maybe see what kind of relationship this was or anything like that? So it's not a direct proportionality, that's for sure, is it? It's not a direct proportionality. So then, what you think is, I don't know, and the shape, what was the shape? I'm looking at this packet here now. Where did you see that shape before? And there it was, right there. So it looks like a direct square proportionality. That means that A is directly, so you're on this side of the equal sign, radius is going to be another side, isn't it? And there's going to be some kind of K, is that right? Now, that's a direct proportionality. That's not what this is. This is a direct what? And so you take the independent variable, do that. Whatever you do to radius, the square of that will happen to area. So if the radius is 1 squared is 1. Well, let's just pretend that, let's pretend the constant is 1, just to make it easy. What if I made the radius 4 times bigger? What's 4 squared? So now it's 4 squared is 16. So the area, instead of becoming 4 times bigger, became 16 times bigger. See that? That's called a direct square proportionality. So here's you said maybe this is true. And how do you prove that? How do you straighten out the curve? You do a secondary graph, and what's the secondary graph going to look like? We're going to put area here, and what else? Yes, because we want to prove that area is what? Say it. Directly proportional to what? Not r, but r squared. And so that's why you did that. Is that how it worked out? Okay, so you had area here, you had r squared, and these units were graph units squared, and what were these? That was kind of weird. What were the units that went down here? Well, radius was in graph units, so what's radius squared? Well, that's interesting. That's interesting because then the slope is going to have what kind of units? Let's try it. Graph unit squared over graph unit squared. What? The slope of this line is not going to have any units. And again, we mentioned this before, that if I were looking into a book, and even though they didn't have this in a book at one time, somebody had to discover this. They said, what is the relationship between the radius of a circle and its area? And what is it? And it's some number that was 3 for a long time. Then it became 3.1 for a long time. Then it became 3.14. Now it's just non-repeating thing that people like to impress people and try to do the first 100 digits of pi. Remember that? And that's more theoretical. And so it should have come out to be, and they thought that's such a special constant in math. They said, we just got to give you your own little symbol. So that's when 3.14 became that symbol like that. Everybody get that? That's really where pi came from. It's the relationship between the radius of a circle and its area. Okay. Probably the most missed question, and again, it's right here. Most missed question is only 1 point, but the most missed question when people turn this lab in is this right here. Everybody know what that answer is? This is a test to prove that the first graph really does show a direct square proportionality. You're right. All right, let's go here. Using the vocabulary, scientific and mathematical, that has been used in class thus far, answer the question. What is the mathematical relationship between radius and area of the square? Now, we know that this is the equation. This is the equation, but how do you say that? How do you say this equation? A is directly proportional to what? Radius squared. Some books would say area is directly proportional to the square of radius. Have that? So you could have said something like that. Area is directly proportional to the square of radius. That would be a good answer. And then so far, you would have had this. That would have been your equation so far. So it says use K. And then give me 2 bits of information. So in the future, every time we do a lab, I'm going to ask you, well, how did you know that? How did you know this was? So what's 1 bit of evidence you said, I'm pretty sure this is a direct square proportionality. I'm pretty sure. What's 1 thing you said? Raise your hand. Tell me 1 thing you said. Here's evidence. It's
When you squared the radius, the slope became a straight line.
when you square the radius and graphed it with area, you mean. So if you graph, you're right. When you graph area versus the square radius, then you got a direct proportionality. That would be a good evidence, yes. The shape of the line. The shape of the line is one of those, possibly that. What's another one?
The numbers game.
The numbers game, even though I don't know how good your numbers were, and again, real scientists don't really play the numbers game like that, but if your numbers were halfway decent, you could have played the numbers game. Like when I made radius 3 times bigger, what happened to area? When I made radius 3 times bigger, what would happen to area?
9.
It would get 9 times the square of that, wouldn't it? Okay, so I like any of those would be good things here. And then down here, show your work for slope, and you just had to pick 2 points on the straight line, right? Not data points, remember that? I know math like to do that because all their points are on the line, right? We can't put data points. So you pick 2 points on the line, and you find the slope, and by golly, it had no units. It had no units, and I think if you came anywhere close to 3, that's pretty good. Did anybody happen to get 3.1? You did? Wow. 3.10?
I got 3.16.
Wow, that's impressive. Anybody else get 3? Anybody else get close to 3?
3.2.
Okay, good.
3.2.
3.2?
I got 3.09.
Wow, that's great. Yes?
Got did 3.
3? Okay, fine. 3 what?
Yeah, I just got
3 even? That's fine. If you got close to 3, you did a pretty good job of measuring, okay? If you got 4, that's up there. You're getting a little bit far away. If you only got 2, that's pretty far away. Everybody get that? If you got 10, something's wrong. Okay, and then the last thing, it says here, what's your final equation? Your final equation should have been this. A equals, and some of you said you got 3.1. You should have had this. You should not have had 3.14 because you had to use your slope into your equation. Get that? I never asked you to tell me what the equation was in a math book. You had to pretend that you were the first person to try to figure this out. So there is no pi. There's no pi yet. And it says here, this is an application question. If you understood what was going on, if a circle's radius goes from 1.5 to 12, then what would happen to the area of the second circle? How many times bigger will it be? And you got to be careful in this because how do you do the first one? You had to put that in your calculator, didn't it? All right, get your calculators. Everybody get your calculators out anyway. How many times larger did the radius get? You all ready? Parker, you all ready?
Yeah.
All right, give me a hit on the calculator. Give it to me. What do you got?
8 times larger.
8? Okay. So, if the radius gets 8 times larger, will the area get larger? Yes, it's one of the direct relationships. Will it get 8 times larger? No, that'd be a direct proportionality. So how many times?
64.
64, which is 8 squared times larger, won't it? You can say to yourself, I don't like that. It's okay if you don't like it. If you make a radius of a circle 8 times bigger than another one, and you were to measure the area, it would be way bigger than 8 times bigger. It'd be 64 times bigger. 64. All right, what do you think? Does that make sense? Learn anything for doing this? A little bit? Okay, I hope you did. All right, let's go back to this. And I had asked you, I'll tell you what, I had asked you to do this on your own, but I think we have enough time for you to do the last one in a small group. We'll go all the way back to page, I call it page 7. Start right here, and this is a weird looking graph, okay? Not really, it actually, all the inverses look like this, but wait, I forget, your class didn't do the last 2, is that right? Yeah. Let's do this one. I'd like you to get in a small group, find out who the independent variable is, and then manipulate it, play the numbers game on the data table, play the numbers game on the graph, don't peek at the next page, and then see if you could tell yourself, if I had to make a secondary graph, what would I do, and what would I put here, and okay, let's do it. Go ahead and meet with somebody. Give you about 7 minutes, 6 or 7 minutes. This is pretty much what you're going to be doing on the test. The test on Monday, this is pretty much what you're going to do is analyze, interpret data.
Yes, that is true.
If you're really, really good at this, you can do the last 2, but definitely do the last one here, the next to last one. Okay, and they call it distance in this area, and they call it height here, so if you want to call that D, you can do that. Now, is it a direct relationship or an inverse relationship?
It's correct.
Okay, now we gotta figure out which one.
Is it in bold?
Yeah. I just said before the test, how to do the last 2, but, wow, you already figured that out?
Well, it's kind of hard to miss.
Well, I understand that, and some people never did do that.
And it looks like
It's weird that,
graph.
that nobody ever looked at or something, but also, on the test, you won't actually have the titles on it.
I mean, like, this one looks like a square root. So, and this one looks like a parabola.
Well, we didn't do it.
Yeah, I did, but you just haven't
We did it in
math.
Photoshop.
Okay, good, yeah, that's good then.
I don't know if y'all got used to it. Oh, I just realized that. Yeah. That was a good thing.
Even though they say distance here and then put H, I think I just. Okay, so now,
It's all we have is
Write this, please write this one.
this one, or that gets, I mean, yeah. So everybody knows this number gets 2.2, so this number gets 5 times.
The square root of 5 bigger than 5.
Or 1 over history.
So don't want to finish it, and I was already did it.
Yes.
Eli, we had 7 questions. I already did this yesterday. Oh, yeah, I did all my thinking on so much math work, but she didn't make I'm gonna start checking all of their homework.
All right, hang on. How about the secondary graph? Figure that out yet.
Ours is Friday. No, but they're not. We have till chapter 43. See, I told you, Clayton. Sarah said we're taking the bull.
All right, let's everybody sit down. Let's everybody go back to your regular seats. You've done a great job.
It's my calculator.
Okay, here we go. I understand, even today, I saw some people who still couldn't quite figure out which one this is, even though the title's right here. And I'm not trying to say that's cheating, but maybe being resourceful is that word. But I don't want you to depend on that, because you're going to have, on a test, you'll have one page, all you see is data tables. You have another page, all you see is graphs. They're not going to have titles on them. Got that? So hopefully you wouldn't look at this and say, do I know how to figure this out? And if you look here, this is a humanized one. So here's your independent variable. And even though you say D here and H here, I'm going to change that to D, make it simpler. But anyway, notice as this gets bigger, so we know it's one of the directs. All right? It's got to be one of the directs. So I get bigger and you get bigger. It's one of the directs. All right, look up here. Now, if I go from 1 to 3, I saw one group do that, and then they had to figure it out. This is 1.7 something, and they said, I don't know what that means. I get it. You happen to pick a weird number, 3, and how many people know the square root of 3? That's why you didn't pick up on it. Now, what if you went from 1 to 4? That made it 4 times bigger, and this got only 2 times bigger. And then you go from 1 to 9. That got 9 times bigger, and the other one went from 8 to 24. It got bigger, but only 3 times bigger. Whatever I did to the independent variable, the square root of that happened to the dependent. Everybody get that? That's why it's called direct square root. Now here's the hard part. I always think this is the hard part. What if you had to do a secondary graph to straighten out the line? Number one, you straighten out the line to prove which proportionality it was, and what else do we get out of that straight line? See if you remember this from yesterday. What else are we going to get from that straight line? Somebody said it. Why? What's the slope going to give me? Yeah, what? The constant. You're right. Very, very good. Everybody get that? Because your ultimate goal is to come up with a mathematically equation for this relationship. And so right here, we're going to have V and what? You say, well, I think that I think this is directly proportional to the square root of D. That's what I think, and I'm going to put a question mark there. So how do we prove it? We do a secondary graph, and we're going to have here V, and what's going to be here? So if you understood square root of D, then let's flip it over. Let's see what happened. And again, they use H here. I'll put a D here. All right, look, here's your first 2 original ones, and they made a new calculated column. See that? And there they goes. And, oh, look, they proved V was directly proportional to the square root of D. Whoops, the square root of D. Everybody see that? Are you guys feeling a pattern? I mean, it's not math class, but we're doing a lot of things with numbers, aren't we? And if you can feel, if you can get the feel for this, there's a lot of things in physics will just come to you just like that because, hey, look at that. All right, now I don't. It's up to you to do the last one on your own. I want you to do one by yourself. And if you have trouble doing it by yourself, you need to come and see me before Monday because we have a test on Monday, right? But if you can't do this by yourself, you come and see me. But we've done 5 of the 6, haven't we? The other thing I really like is this page that has a summary. And I'll tell you, again, I told this before, I wish somebody would have taught this to me before. I never had this in high school. Nobody taught this to me in college. I wish I would have known it. So let's do these again. Notice the pattern. Direct proportionality, the graph looks like that, right? Look at what's the equation look like. I'm on this side, you're on that side. Who gets the constant? The independent variable. Y equals mx. Slow it down a little bit. All right, how do you find k? Slope of the line. What does it mean to be directly proportional? If b were to get 4 times bigger, a would get what? 4 times bigger. If b would get 9 times smaller, a would get 9 times smaller. Then we go here. We had this one. That was the thing you took home last night. This curve. This is what that graph looks like, a J-shaped curve, and it says A is directly proportional not to B, but notice they're on the opposite sides again. See that? See the pattern? And how about the one you just did? How about the one you just did? What am I got right here? A equals KB. A equals KB squared. A is KB. What? K. Oh, the pattern. Everybody see the pattern? What's this graph look like? Like that? And how would we straighten out the curve? A and what? Root B. And again, the slope would be your constant. All right, what does it mean? Here we go. You do it. Help me out. If B were to get 4 times bigger, if the independent variable got 4 times bigger, let me just see if there's anybody who maybe doesn't catch on here. Raise your hand if you're not 100% sure what's going to play here. So I'm not 100%. I'm only 80. Anybody? Really? All right, Ben, you help me out, right? If B were to get 4 times bigger, we know that A has to get bigger because it's one of the directs. All the directs, I mean, if you get bigger, I get bigger, right? So we know it has to get bigger. So what's A going to do? Is it going to get 4 times bigger, 4 squared times bigger, or the square root of 4 times bigger?
Square root.
And what is that? Square root of 4.
2.
Get it? So if we had these 2 variables talking to each other, if they could talk to each other, watch. Hey, I'm going to get 5 times bigger. Me too. I'm going to get 10 times bigger. Me too. Hey, you're keeping up with me. And that's why the line's straight. Watch here. They're talking here. I think I'll get 4 times bigger. Well, I'll get 16 times bigger. What? I'll get 10 times bigger. I'll get 100 times bigger. What? I can't keep up with you. And that's why it curves. And then we go down here. Is this okay to talk like this? I'm not in drama class, but ready? Rich, I'm gonna get 4 times bigger. I'll get bigger, but only 2 times. Well, I'm gonna get 9 times bigger. I can only get 3 times bigger. I'm gonna get 100 times bigger. Oh, I don't want to get 10 times bigger. You're going too fast for me. And see how it curves that way? Okay. All right. Well, anyway, what about this one? What if B were to get 9 times smaller? Watch, Ben's going to answer this. Ben, what if the independent variable got 9 times smaller?
A would get 3 times smaller.
3 times smaller, because it's direct, isn't it? Direct square root. Very, very, very good. You okay with that? And I'll bet, even though I'm asking you to do it by yourself, I'll bet you can see a pattern here. Same side of the equation. AB equals K. Inverse proportionality. AB squared equals K. Inverse what? Inverse what? You're not seeing the pattern. You're not seeing it. AB equals K, inverse. AB squared equals K, inverse square. What's this one going to be? That's right. Everybody see that? All right, and real quickly, what would I have here? The one you're gonna do it on your own at home, what are you gonna put here? Yes? And I know somebody said, poison, your math teacher said, poison, don't put a radical in the denominator. Why? They just don't want your answer like that. You see that? Just sometimes I tell you, put your answers in 3 sig figs. Why? It makes it easier. It's not like there's anything wrong with it. That is what I'm going to do, 1 over root b. Okay. And you can finish that too. Now what I'd like to do, I would like to start the last part of the lesson. And so we'll do that today. And you'll probably finish it on your own maybe tomorrow. We'll see. I'll let you have some time to study tomorrow. I'm going to show you, we're going to phase into you doing experiments. And so if you had to do an experiment, you say, well, how do I do an experiment? Well, you want something that's going to generate data. So let me go ahead, oops, here. Let me show you a quick one I did. And actually, it led somebody to do an extra credit project. There it is right there. Okay, so how fast can we generate data in an experiment? Let's try one. I have a meter stick, I have a ball. See? Okay, now, watch. Generate experiment, watch. I can already generate 2 or 3 experiments right there. How does the surface that a ball bounces on affect the height that it bounces? How about that? Can we do that? What's another way to do it? What if we want to keep the same surface? Could we say, how does the height that a ball will drop from, what relationship does this have to the height of the bounce? Can we do that? And that's the one I picked. And so what I did is, can you write down some numbers for me just anywhere, and just maybe in the margin or something like that? All right, so, ready? You're going to help me generate some data for me, right? Now what I'm going to do is, I'm going to, you have to get your eyeball where you want it. So I'm going to drop it. I'll say 1, 2, 3. And I'll drop it. 1, 2, 3. Now you have to get your eye close to this. Now, when you do an experiment, we have to have some things called operational definitions. Operational definition says, I hereby declare that the height that I drop it from is defined as what? And that's what you're saying, the height on the meter stick. The height of what? The height of the ball? Which part of the ball? Middle of the ball? Yeah, I like the middle of the ball. You do? What do you do down here? When I bounce it from 0, your definition says the height is not 0. Is that, you want that? So I have to think about that, don't I? I think I'll use the bottom ball. I hereby declare that the height that I drop it from is the distance from the table to the bottom of the ball. Everybody get that? That's my new definition. Now, what you're going to do is, I'm going to drop it, and you see this? You're going to put you might have to stand up. Okay, what I'm going to do is, I'm going to drop it, and, ready? 1, 2, 3. 1, 2, 3. 1, 2, 3.
5, 7, 6.
Oh, I hit my thumb. No good, no good. 1, 2, 3. All right, tell her what number you think she's ready.
Let's go 72.5.
Okay, now if we were doing this for real, maybe if I had a camera set up and I could do some slow-mo, I think these are really good numbers, couldn't I? All right, so say 100, I dropped it from 100, it bounced to what, 70 something? All right, ready? Let's drop from 80. 1, 2, go. 1, 2, go. Notice I'm dropping it the same way every time. 1, 2, go. 1, 2, go. 1, 2, go. So if I do a real experiment, I might do this several times and do an average. So what do you think? Give her kind of what it is.
59.4.
Okay, let's do another. Drop from 40. Ready? 1, 2, go. 1, 2, go. 1, 2, go.
Oh, that one was 6. Your hands count.
Okay, sorry. 1, 2, go.
Oh.
1, 2, go. You only look at the first bounce. 1, 2, go.
Right. 30.7.
All right, so anyway, what's going to happen is we could generate an experiment like that. So it didn't take very long to do that. All right, now, what I'm going to do is, can you give me some numbers, give me those numbers, okay, what is 100, when I dropped from 100 to what, 70, 72, when I dropped from 80, it was 59, and I dropped from 40, it was about 30, okay? Do you understand there's a pattern there? Did everybody get that? Okay, so there's a pattern. So, what do you think? I don't know if you ever watched Price is Right, but sometimes they have them games where they have a little sliding thing, and if you get anywhere within the sliding thing, you win the car. You ever done that? You ever seen those? They have like the price of something is here, with this little sliding bar. When it stops, if the price is somewhere in there, you win it. See that? That's what Tucker's gonna do. Tucker, I'm gonna give you $1. If you can tell me, I'm gonna pick some random thing. If you can tell me about where you think it's gonna bounce, and then the audience will help you, and they'll say higher or lower like that. Okay?
Yes.
So what we'll do is, if you can get, all right, if you can get within 10, if you can get within 10 centimeters, you get the $1. Okay? I'm gonna drop this one from 70. So you can ask Jessica to help you out with. What is the slope? What do you think the slope's gonna be? What was the y over x? What was that? 70. Take that and divide that by 100, and then give Tucker a little help here. Take the smaller, divide by the big number, and tell him those numbers. Okay, now ready?
Don't blame me though.
What kind of numbers do you get? Like point? Listen to the numbers.
Get all of them, it's around like 0.7.
They're all about 0.7? Okay, so this thing should bounce about 70%. So if I drop from 70, where do you think? You put your hand there, and we'll see if you get it, okay? So make a little bar here, make a 10 centimeter bar. Where do you think it's gonna go? Okay? Okay, ready? All right, let's see if he gets $1. Everybody get it? So you're predicting somewhere between 50 and 60, right? Everybody ready? Here's 70, and ready? Go. See, I don't like losing $1. But yes, I switched balls on, okay. But I don't like losing $1 across. But what I did is, you know that they make these two balls, and they buy them in the set. And they're actually called the happy and unhappy balls, and you can probably figure out which one is happy. Here's your happy ball, and here's your unhappy ball. And you can do all kinds of things with this. I even had a person do an experiment a long time ago, and they didn't bounce on a table, they bounced on a carpeting. Interesting, when you bounce on a carpeting, it's a different results. And the dad happened to be a dermatologist, and they have all kinds of liquid nitrogen. You know that? But they always freeze off things, okay? So they actually exposed these to really cold temperatures and got a different result. I thought it was a great experiment that person did. Okay, sorry about the $1. If I do find $1 one day, I'll give it to you.
Oh.
But you did not guess it. But if we take a look up here.
Look out.
Okay, now.
No, all these game shows, every game like this, it's always rigged.
Yeah, exactly.
Always rigged.
Price is right.
It's always rigged, Tucker.
All right, so let's take a look. Yeah, I got to hurry a little bit here. Okay, now watch. This experiment was height bounce versus height dropped. Everybody get that? And so we can actually come up with an equation. All right. First of all, it was a direct proportionality, and this person they decided to do a lot of different sports balls, and they came back and did the bouncy ball. They did a basketball. They did a golf ball. They did a wiffle ball. And that's what I liked about it. That was a really good extra credit experiment. And they did each one of them 3 times and found the average. You see that? Anyway, so they did a really good job on their data. Then they found the slope. They found the slope, and they got 0.82 and 0.61, but the slope had no units. That's interesting. Because, and I know in math class they never do, but in science they almost always have units. Remember grams per cubic centimeter? The slope was actually density. Or miles per hour, the slope was actually speed. Grams per penny, remember that? That they actually did have units. Now, what happens in science when your slope does not have units? And I wish somebody would have taught this to me, because I went to college and I remember doing some labs, And they said, well, the blah, 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 blah was 0.55, and the other one is 0.865, and I didn't know what they meant. It's just some number. I didn't know what they meant by those numbers. But I want you to know that. What do you think it means when, I'm going to call this the index of bounciness. I just made that up. I hereby declare that the index of bounciness for the wiffle ball is 0.482. What does that mean? Uh-oh. Yeah, when there are no units, what happens?
Well, it means the proportion between how high you drop and how high you bounce is 0.482. If there's no
So,
units.
wait, say it one more time.
So like, if there's no units, then you don't, like, if you don't have units, then you just know that for every, like, one it bounce, for every one you drop it from, you get 0.482.
What does that mean? That'd be like saying density. Well, for every 5 grams, you get 1 cubic centimeter. Tell me, it meant density was 5, right? 5 grams per cubic centimeter?
The slope is 0.482.
So what does this one mean? When you don't have units, what does it mean?
You don't have units, what does it mean?
Yeah. What do you think?
It's just a ratio.
It is. All slopes are ratios. Yes?
The wiffle ball will bounce 48.2% of the height that it was dropped from.
And I wish somebody would have taught that to me, because this looks like a real scientific thing. I don't know what you mean by 0.482, but what is 0.482 with no units? That is the same as what? 48.2%. On that surface, in that room, that ball, that wiffle ball, should bounce 48.2% of the height that it was dropped from. You get that? Everybody see that? And you're right, it's a ratio. We can divide both sides by HD. What is the height bounce per height drop ratio? 0.482, also known as 48.2%. So if you do an experiment and you don't have units in your slope, you're probably in the world of percent. Now, we just got done doing a lab, and you came up with a slope of 3.14, no units. What does that mean? Yes,
Radius is 3.1.
the area.
I was gonna say the radius is 3.14% of the area. That's not right.
No,
Say it's
3.14 is what percent? 314%. Isn't it? Isn't it?
Yeah.
314%. Maybe you remember this. You remember the circumference of a circle's diameter times pi? Did you know that means that every circle in the universe is 314% longer than its diameter, which is 3.14 times. And that's what that means. So I wanted to show that to you, to show you how to generate data, how to do an experiment, how to do operational definitions, that kind of thing. And I've had people do this. I've had people go down and really get into this and make a poster, and they have a picture of basketball, and they really got into it. And they were willing to put the time into it, and maybe they dropped it the same, and maybe they had somebody else read it, or I don't know if you want to use your camera. That's another thing you could do. All right, so we're doing application now. So let's get into application. And here we go. I pulled this out of one of Paul Hewitt's older books, and we need to talk about this a little bit. It's a weird thing. He made it up. It's called a butter gun. And so let's talk about the butter gun. And you can read this. It talks about the butter gun. Notice what happens in the butter gun gets to blah, blah, blah. So here's what's happening with the butter gun. In a butter gun, if you were to pull the trigger, and here's a tray that can hold 1 piece of toast. So 1 piece of toast can be there in this tray, and then when you squirt it, it will exactly cover the bread. And how thick? And the thick, it'll be 1 millimeter thick. So when you're at this far away from the butter gun, I made a little chart here, distance and thickness of butter and number of pieces of toast. Let's take a look and let's generate some data here. Ready? When the distance is at 1D, let's call it 1. The distance is 1. I can exactly butter 1 piece of toast, and the thickness of the butter is 1 millimeter. Now, watch what happens when you move this device twice as far. So the distance got what?
Twice.
2 times bigger. What happens to the number of pieces of toast that can be buttered? How many? 4. But how thick is the butter on each piece of toast now? When was it? Yeah, 1/4 of what? 1/4 of a what? 1/4 of a millimeter. Right. Now, let's move now the butter gun to 3 times the original distance. 3 times the original distance. What do you think? How many pieces of toast now?
No.
And what's the thickness of that? How much? 1/9 of a millimeter. We can put that in decimals. Here we go. Let's make an equation. Ready? How is the thickness of the butter related to the distance? Oops. Uh-oh. Wait a minute. I should have done that. All right. As this gets bigger, this gets smaller. So thickness and distance as well. On the same side or opposite side of the equation? What do you think? Same? On the same, right? Now, we don't know, this is my independent variable, by the way, okay? And that's going to equal some constant, right? Is that right? Now, is it a plain old inverse proportionality? Take a look. This gets 2 times bigger. This gets what? What? 4 times smaller. It's got to be one of the inverses. Which one is it? Whatever you do to the independent variable, the inverse square of that happens, which is what? It goes to 4 times smaller, doesn't it? What happens if the distance gets 3 times bigger? The thickness goes to 9 times smaller. Inverse square. So if I were to sketch that graph, and here's distance and here's thickness, it would go inverse square. What's that look like? And all the inverses have the same shape, don't they?
Yeah.
Now, there's another one up here. There's another relationship here. What's the relationship between distance and number of pieces of toast? Let's try it. As this gets bigger, this gets bigger. So I'm going to put on the opposite side of the thing, number of pieces of toast, and this is going to be distance. There you go. Now, is it plain old? What is it? Is it plain old direct proportionality? Let's take a look. As this gets 2 times bigger, this gets
4 times.
well. As this gets 3 times bigger. So what is that? Direct what?
Square.
Direct square proportionality. And what would that graph look like? Pieces of toast versus distance. What would that graph look like? What's direct square look like? You just did a lab on that. You just did a lab. Jay. Ooh. So the reason they taught the butter gun in his book is they thought you could understand inverse square and direct square there. And so what I have here, I want to show you some more things today. I only have about 3 or 4 minutes, but take a look here. Gravity. Gravity is an inverse square proportionality. I'm going to tell you it's inverse square. Got it? Now, when you're standing right here on the earth, where is the center of gravity? And I'll tell you right here, it's not on my table, because I've moved the table, it keeps going down. So where's the center of gravity? It's down there, way down there. As a matter of fact, it's about 4,000 miles away from me right now. I'm already 1 Earth radius away. I am 1 Earth radius away from the center of gravity. And let's say somebody weighs 200 pounds on the Earth's surface. Now, if I were to take you another 4,000 miles away, now you're 2 Earth radiuses away. Get that? So distance got 2 times greater. How much are you going to weigh? It's inverse square. As the distance gets greater, my weight gets smaller. But how much? If the distance goes from 1 Earth radius to 2 Earth radius, distance got 2 times greater, my weight will get 4 times. And what is 4 times smaller? Use a reciprocal, 1/4 of what you used to be. How much will this astronaut weigh? 50 pounds. Now, by the way, even though if you get further away from the Earth, you do weigh less, that has nothing to do with why astronauts are weightless in space, because they are only 100 miles away, not 4,000. If you're 4,000 miles away, you still weigh 50 pounds. Don't tell me that's weightless. Being weightless in space has nothing to do with you really being that far away in orbit around the Earth. Okay, let's do one more. What if I were to move here? All right, here's 1 Earth distance, 1 Earth radius, 2, 3, 4. If I move 4 times further away, if the distance gets 4 times greater than it was, then what's my weight going to be? Inverse square. What? Inverse square what? Oh, I lost you. If the distance gets 4 times greater, the weight has to get 16 times smaller. And so what is this divided by 16? See if we can find that out. What's
12.5.
Okay. So if I moved and I'm all the way here, now I'm 12,000 miles away from the Earth's surface and another 4,000 miles there. I'm 12,000 miles away from the Earth's surface and I still weigh 12.5 pounds. You're still not weightless. So again, I'll teach that later. Why are astronauts weightless when in orbit? It's not because of this. All right, 2 more quick ones. What I'd like you to do for homework is I'd like you to go through this packet, and I want you to read this and just figure out if you can understand what these are. These are inverse square proportionalities. Okay. All right, thank you. That's going to be enough for today.